Hello, brother. Today we want to explain the demand side management project and optimization system and how the code is operate. The first thing is there is about four or seven code, MATLAB code in the single code. We want to explain the base case, the first case. The first thing is the code. The first code is the main program for the base case without demand side management project, and optimize the unit commitment and economic dispatch using LAPC optimization method. The only thing for that to clear all the screen and the command window and all the parameter in the workspace here. And after that, we call the APC program. The APC program we will explain in the next video, but the first thing we will explain the sub code MATLAB that code dependent on like the load demand. This is this is two column here. The first one is the time, the hour for 24 hours, and the second thing is the load demand in the kilowatt. And the second sub code sheet here is our power output from the solar. And for the solar, there is 4 scenarios, and each scenarios, this is the power output from the solar kilowatt. And the next sheet is for the wind power, output power. The first is time, and the second power output for each scenarios. And as you see here, this is the output from the wind power as it is. And the next code is the market price. And the market price is dependent on the time, during the time is changing during the time. As you see here, for 24 hours, and the market price in euro per kilowatt hour. This is the MATLAB file that code is dependent on the load, solar and wind and market price. This is all the code is constant, and there is no comment. In the next video, we will go to the next code, optimization code, and the object function. Hi, this is the next video for clarification of the code, base case code. And this in the base case code, the next code is the optimization function, artificially Bee Colony in MATLAB. So the first thing is to call that from the main program, and after that we have some problem definition or parameter definition, like the number of decision variables, the decision variable matrix, like this, how many the number of decision variables in our optimization code. And then there is the lower band of a size of these distributed generation. So this is the first decision variables. The decision variables, it's dependent. It's the first thing is to unit commitment 1 1 or 0 0, as you see here. This is for unit commitment, and the second thing is for the capacity of the generation 1, generation 2, and the batteries, as you see here. And the this is the decision variables. This is the lower band or the lower limit, and this is the upper limit or upper band of the distributed generation. And after that, this is the ABC settings and parameter definitions, like the maximum iterations, like the population size, colony size, the number of on-local P's, and some other parameters, acceleration coefficient, and after that we defined the program requested from the user to enter the number of scenarios that you want to optimize. And then we initialize some variables, as you see here, the MTP structure and initialization population array. and initialization best solution ever found, and create initial population, and after initialization some variables, we started to initial population, as you see here, as a randomly position for each decision variables. So in this program, the first thing is here to initial population is randomly uniform randomly values for each position. That position contain, as you see, as you mentioned before, the status of each generation and the value of the megawatts from the generation and batteries. And after that, as you see here, we put it in the object function demand side function, as you see here. And the demand side function has two input. The first input is the optimization values, and the second input the number of scenarios. And the output from that is the cost of this population or position, and the new decision variable status and values dependent on the demand side object functions. And after that, we compared with the cost with the best cost here to store the best position. So in the first, as you see here, for each iteration, we should to store the best one, the best position. And after that, we also compare with the best solution ever for all the thing. We compare if the population cost is less than the best cost. We store the values of the generation and the cost of a new population cost as a best cost. And this is repeated for the number of population, as you see here. And after that, we also initialize some counter and some array to hold best cost values to plot the figure of convergent graph. This is the first part of this optimization file, and the next videos we explain the main loop of the optimization function. Thank you very much.